In the early 1670s, Christian Huygens formulated a principle of light waves, stating that every point on a wavefront is a source of new waves. And in 1801, despite the prominence of Newton's rival corpuscular theory, another Englishman, Thomas Young, proved beyond a shadow of a doubt that light is a wave. He accomplished that by proving that light has the wave property called interference. Wave interference can be seen to be constructive or destructive. If the waves, as they travel, encounter each other in step, they can reinforce each other, create a stronger wave, and produce what's known as constructive interference. But when they're out of step, waves can cancel each other completely. In other words, destructive interference. As Thomas Young suspected, all waves in all media behave in this fashion. And to prove that light is a wave, he merely had to illustrate that light exhibits interference, the behavior common to all waves. Here's the principle. Light from a single source enters two slits, which are side by side and not much farther apart than the wavelength of the light itself. After passing through the slits, the light shows up as a distinctive pattern on the screen. When a single plane wave encounters two slits, each slit becomes the source of spreading wave fronts. And because both new waves originate from the same plane wave, their oscillations are synchronized. The result is a stable pattern of up and down ripples, alternating with directions along which the waves cancel one another. This produces a pattern of bright fringes of constructive interference on the screen, separated by dark fringes of destructive interference. And that was it, a series of alternating fringes to prove that light is a wave. It was a conclusive demonstration, and ever since, physicists have had to explain the behavior of light in terms of the properties of waves. For example, if light waves, like all other waves, bend around corners, how can it be that light can cast a well-defined shadow? The answer can be found in the relative magnitudes of the wavelength of the light and the size of the opening through which it passes. The shorter the wavelength, the less completely the wave spreads in all directions. Even with a wavelength equal to the width of the opening, the beginnings of a shadow can be seen. The shadow is really due to destructive interference of light from different parts of the gap. And the result of it all is, the shorter the wavelength, the more nearly the light emerges in a well-defined beam. The wavelength of visible light, hundreds of nanometers, is so small compared to the sizes of normal objects that they can cast very sharp shadows indeed. But that explanation doesn't shed much light on an even more important question. Since everything ever seen is the result of light encountering matter, the question is, what is the nature of that encounter?